We're moving on to the second of 3 topics that we cover in this class. We're done with limits now. Well, we're not done with them, but we're done teaching about limits because you've already learned it. And now we move on to the second topic, which is differentiation or derivatives. We'll spend probably the rest of first semester, if not more, in differentiation because it's kind of important. And then we'll move on to the third. Okay, so a lot to do today. A lot of terminology today. Well, here, let's do this. Yeah, we're going to talk about that. That'll be great. So we're going to talk about the difference between tangents and secants. So a little bit of geometry today as it relates to calculus. We've got slope of a tangent line. You should all be experts at finding slope because you're in calculus. We'll talk about the definition of a derivative. What exactly is a derivative? How do we find it? How do we find the value of it? We'll talk about differentiability, that's a big word, and continuity. We did continuity already, but we're going to talk about how the two relate. When is something differentiable? If it is differentiable, is it continuous? If it's continuous, is it differentiable? That whole thing. And then you should be able to hold your breath for 45 seconds. Ready? Hold on. Okay. I'll count down so you can get your breathing under control. 5, 4, 3, 2, 1, go. Well, that was 4 seconds. Good job, Samantha. That's 10. Hold my breath for 45 seconds. Okay. 1/3 of the way done. No cheating through your nose down there. This is a good video, isn't it? That's 30 seconds, 15 left. He's struggling. Come on, Alex, you can do it. Eyes on the prize, buddy. Time. Nice. Who made it? Raise your hand.
I was like a 3 seconds under
I know you really struck out. You had the side of your head starting to get bigger and bigger. Okay. By the way, the world record for holding your breath that was 45 seconds. It's 7 minutes something seconds. So you got a little bit of work to go on that one. Okay, so tangent line versus secant line. Tangent line is the line that intersects a function in exactly one point. Now here's some new notation that we're going to start using. Obviously we're talking about a function f of x. Instead of talking about the points on the function being x comma y, we're going to get used to using this notation, which is x comma f of x. Long-winded way of saying we're changing y to f of x now, because that's the big people way to do it. Okay, so no longer xy, instead x f of x. It's the same thing. You put x into a function that spits out a value. That value is sometimes called y, but for us it's going to be called f of x. A secant line, however, excuse me, intersects the function in at least 2 points. Could be more than 2, but it's got to be at least 2. So it says up here more than 1. More than 1 is the same thing as at least 2. So I got a little demo for you. And later in the slideshow, I have a still picture of, why can't it open this specific one? We are currently experiencing technical difficulties. Please stand by.
Just makes this video accessible.
There we go. That's what I wanted. Okay. I have a still picture of this on the slideshow, so if you want to go to the slideshow and take a picture of this, instead of trying to write this down or draw the picture, it'd be easier just put a picture in there. Let's talk about what's going on here first. So I've got a blue thingamajobber that's a function. It's probably a cubic. I don't remember what I used. And I put 2 points on that curve. I've got P over here, which relates to x. So I chose a value x, and that generated the point P, and therefore the y value of that point is f of x. You with me? That would be the yes or no portion. Yes. Good. Yes. Then I moved over some distance. How far did I move over? I moved over delta x. ooh, delta x, we've seen that before, to this new point, x plus delta x. So I can choose this x to be anywhere. I just happen to pick it on the left of the y-axis, but I can put it anywhere. And I can have delta x be any distance. That generated a new point. Here's q. So I went up from x plus delta x to q, which gave me the y value of q being f of x plus delta x. That look familiar? Good. It should. That rhymed. You can't think of another word that rhymes with could and should. Would. Hood. Dood. Food. Good. Hood. Would. Would. Mood. Mood's not a word, is it? Where am I? Okay, so here. I've got a tangent line through P. That's the red thing. I've got a secant line through PQ. And it hits in 1, 2, 3 points. Okay, and that can change as long as it always hits in 1 point. We good so far? Question?
How do we know it only hits at one point if the red line continues up and then the blue line continues?
Because I told you and I would never lie to you, Connor. I would lie to Greg, but not to you. Yes, Greg?
In that case, I have a question. Is delta x always going to be positive?
Yes. Even if we move delta x to the other side, it's still a change, and that change is not dependent on a sign.
I don't know if I trust that answer.
You said you
Is that a lie? That counteract that.
Well, if you ask me if that's a lie, then therein lies another problem, because if I lie, then I would lie to the answer and say no, but you wouldn't know if the answer to the question if I lied was a lie in fact, which would then negate what we just said. So,
Okay.
But counteract.
Are you in the vegetable period?
It's a
I
nice
think
fashion
last-
accessory.
doesn't it look, it looks good, right?
It looks like power move.
I mean, that's okay. Matches the black and the gray. It's not like I'm wearing a green shirt, then it would be like fashion faux pas. So I thought and it fits. I got a little breathing room in here. Anyways, okay, keep that in mind.
Oh boy.
Okay. So what's the slope of PQ? You probably need the picture, right?
Yeah.
I was afraid of that. All right, there's the picture. What's the slope of PQ? Want some help? Greg?
Is it f of x over delta x plus delta x?
Wait, I lost you there. Is it what?
Oh wait, I don't know actually. Is it? I feel like it's the equations we always see. I feel like this might be wrong, but is it f of x plus delta x minus f of x all over delta x?
It's not horrible. Let's give it up, huh? Well done. All right, so I'm going to get there in a roundabout way. We'll start with the simple slope equation. You all know that, y2 minus y1 over x2 minus x1. And then when we plug in, we get that. Right? And Greg was smart enough to realize that if you look at the denominator, what's going to happen to the x's? They go away, and we get that. Okay, good, well done. That's the slope of the green line, the secant line. What's the slope of the red line? I don't know either. How do we find the slope of the red line? And we need it. Yeah, I don't have another point.
Plug in 0.
When in doubt, plug in 0. Mark, ideas? Okay, so I'll give you a hint. It has to do with calculus. Was that sarcasm, mister?
You find the limit.
Oh! The limit of what?
A red line.
Limit of x.
Ooh is ooh no. No. We're getting there though. Limit is a good idea.
You get the limit of where x approaches 0.
Oh, so close. So close. Because if x approaches 0, I'm just going to move that guy over there.
Yeah.
That's not real exciting.
X approaches p.
X
The
approaches
limit
q.
as
X can approach P.
X approaches q.
X approaches x.
If X moves over here, Q's going to go with it. It's like, never-ending race.
Okay. Is
X approaches X.
It's already at x.
X approaches delta.
That was fairly zen of you. When x is at peace with itself. Patrick.
When X approaches X to the negative or to the positive?
No.
Oh, damn.
No.
Limit as x approaches f of x plus delta x.
Say again?
Limit as x approaches x plus delta x, or f of x plus delta x.
We're getting warmer. I know the slope of the green line.
Yeah, the limit is the slope. So
As X approaches
X
the-
approaches the slope for the.
Correct. We want the limit of the slope, but what we don't know is what's approaching what. Because when we take a limit, we need to know the limit as blah, blah, blah approaches yada, yada, yada. So what's blah, blah, blah and yada, yada, yada?
When X approaches that whole mess.
Nope.
Let's talk about the terms. It's good vocab, yeah.
Nothing?
No, we got squat.
Okay. I want to find the slope of the red line. That's the goal, right?
Yes.
So in order to find the slope of the red line, I'm going to cheat, and I'm going to turn the green line into the red line. How do I do that?
Something with calculus.
Something with calculus. Excellent. Good. Mary?
Do you find where they're like continuous? Or what's it?
I don't
I
know.
forget, like when they're, it's like where they both, oh, I forget where I'm going with those.
Are you trying to use the word contiguous versus
Probably not.
continuous?
So yes. Yeah, yeah,
Yes.
yes. Just say yes.
Okay, you're right.
Okay.
How do I do that?
It was like in the last chapter where you find like as it approaches from the left and right, and then
Too much work.
yeah. I don't
Yeah.
know.
Okay, I'll show you a picture of what happens.
You have a picture.
Whoosh.
Oh, you make it perfect?
It slows down there because we got all the time in the world. Yeah. Mm-hmm. Oh, the excitement is overwhelming.
Oh, because Q
Almost. Here we go. It's kind of anticlimactic, right? You're expecting something to happen, like confetti shoots out or something like that. All right, so what changed? Now I can find the slope of the red line by finding the slope of the green line because they're the same line.
What?
Do you all agree, right? I made the green line into the red line.
It's the same thing.
Correct.
Yeah, but how'd you?
So if I can find the slope of the green line, again, I can find the slope of the red line. And how do I do that, Mark?
No, I have a question.
Oh, okay, good.
How did you make it the same way?
Magic. I slid I slid Q along the graph until it ended up where P
So I
was.
don't have to be like math.
Wouldn't it be nice if they just had a button on the AP test? There you go, and then you watch it slide. Yeah, it's coming. Just wait. iPads, they're amazing. What do you want, Maggie?
Is it as Q approaches P?
Or as P. X approaches Q.
Yes.
As delta x approaches 0.
Nice. There it is.
Wait, is it? Wait, no.
Okay, so what? Wait, right? What do you mean doesn't make any sense? Hold on.
Oh, I get it. I'm getting nowhere.
Whoop, I didn't want to do that.
Undo.
I don't know if I can. All right, watch again. Watch again. What's changing as Q moves down the function?
Delta X is getting smaller.
Delta X is getting smaller. How small do we want delta X to be?
0.
0. Okay, so while that's doing its thing, back to you, Michael. So you said we're going to take the slope. Why am I talking so loud? We're going to take this. Are you bleeding from me? Her hair like. We're going to take the slope of the green line
Yes.
and take the limit as what approaches what.
As delta x approaches 0.
Perfect. Okay, that will give us the slope of this tangent line. Proud of you guys. You did a nice job there. I don't know if I gotta start this line. We did the slope.
We did limits first.
We did that already.
I,
Yeah, so, okay, then it becomes tangent line.
That's a
Uh-huh.
good
Yeah,
example.
yeah, great, took a limit, yeah, you got that. Oh, there you go.
Thank you.
Okay, slope of the tangent line, which is that red line, is found by using this thing, which we've worked with already, okay? Called the difference quotient. We take the limit of the difference quotient as delta x approaches 0. There was a reason why we were working with that thing. It wasn't just, let's see if I can find a nasty equation for them to plug and chug and then take the limit of. It actually solves a purpose, or serves a purpose for us.
Half of you wanted just to
I'm-
mess this up.
I'm sorry, what?
Half of you just wanted to mess with this.
Yeah, well, a little bit. There was a little inkling back there. Yes, Greg?
I'm so lost.
You're in 334.
Math wise,
Oh,
yeah.
where did I lose you?
As soon as
Because you, hold on, let's back up. You gave me this,
Yeah.
so you're okay there.
Yeah, but
And my ultimate goal was to find the slope of the red line.
yeah, but if I delta x as it approaches 0.
I'll get there. I can't find the slope of the red line because I need 2 points and I only had 1 point on there because it's a tangent and a tangent only gives me 1 point. You with me?
So we were just finding the equation right there.
This business will allow me to find the slope of that red line that only has 1 point.
Okay.
It would be nice if we could just use some algebra 1 stuff and do y2 minus y1 over x2 minus x1, but I don't have a second point, so I have to come up with something crafty, which is this guy. Does that help?
A little bit, yeah.
Is this like the general equation? Or is this just for this example?
Oh no, this is general equation.
Okay, and this
Because
is
we
the
do
general
this.
equation.
Well, we'll do the example. We're eventually going to find out this.
So this is the general equation for the slope of the tangent line?
Right.
So
This is probably one of the more important equations you'll get all year, and I'll summarize that in a couple slides after we do an example. Go
Was
ahead.
the other one the slope of the secant, like the official
Correct.
one?
Yeah, that was just a plain old algebra 1, y2 minus y1 over x2 minus x1. Okay. But that does bring up a good point. If you lose this limit part, then that's just the slope of the secant line. You stick the limit on it, and we have the slope of the tangent line. Gesundheit. Okay, are we good on this so far? So now let's look at an example.
You say that last part one more time?
Without the limit,
It's the secant.
it's the slope of the secant line.
Okay.
With the limit, it's the slope of the tangent line. Okay, so now we should be able to do that with a function. We've got a parabola. And I want to find the slope of the tangent line at a specific point on the parabola, 440. So I did some early work for you, and I already told you what the y value is. Some of the problems, they won't give you the y value. You need to find it by plugging 4 in, but we don't have the time to do that kind of business. Two things. Well, let me start with this. You will hear me say this a gazillion times. What do you need for the equation of a line?
X and Y.
What's that?
An x and y.
Nope. A point and a slope. Okay. Over and over again. I'll say that over and over again. So when we get to this step B, you will need a point and a slope. First things first is in part A, we need to find the slope of that tangent line. Okay, you ready? So here we go. There's that mess. Somebody tell me where that came from.
The equation.
Plugged in.
Went to the function. Wherever I saw x, I put in x plus delta x. Put in x plus delta x. So this business to the left of that minus sign is all f of x plus delta x.
Why?
No, x.
Why did you put an x plus delta x?
Because the function, or the equation is asking us for f of x plus delta x. Let's back up.
To find the slope of the tangent.
Yeah, we're going to. We're looking for a slope of the tangent. So this is the first stuff, f of x plus delta x,
Oh, okay.
minus the function. So coming back here, cha 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 cha. Okay. F of x plus delta x minus parentheses important f of x all over delta x. We good? Any problems?
Not yet.
Not yet. You have little faith. Multiplied that bad boy out. Just a square. It's not that difficult. You can do that. You're all smart. I'm pretty sure. Did some more math. What did I do from step 2 to step 3? No canceling yet.
Combine like terms.
Three.
No, did I combine like terms?
No, you distribute.
No, I distributed a tree.
You distributed three.
The tree, right.
Yes.
That's what my grandfather would say. Tree. This many. What next?
Combine like
Or
Mhm.
cancel.
Combined like terms are canceled. We'll wrap that all up into one. Whoosh. Am I going too fast? Should I slow down? Just a little. What do I do next? How so, sir? Who's talking? You or him?
I said the first, you said the second.
Oh, it's like a tag team.
Divide by delta x.
Not yet.
No.
Factor out delta.
Factor out of delta x. Now what?
Divide by delta x. Or cancel.
Cancel. Whoosh. Now what?
Plug in zero.
For
Delta
delta
x.
x. Okay, now this is what bothers some people. We don't get a number. We get an equation.
How do you get the equals 6x minus 2?
That's the limit. Putting 0 for delta x, the 3 delta x goes away, left with 6x minus 2.
Oh, okay, I thought
Okay.
you said equals.
All right, so before we move on, or before I talk about this, is everybody okay with this?
Yeah,
should be minus
Wait,
nine.
or no, shouldn't it just be 2 because the 2x in the, I'll call it step 3 cancels out with another one, so in step
Yeah, you
4
drop-
it
you
should
drop
be
the
just
next.
2.
What?
No,
Shouldn't it just
No,
be
no,
2?
No, it's
that's
a
why you
typo.
didn't mean to put the x.
yeah,
second
the x
last.
is,
It's
the
just-
Yeah,
minus
that's
2x
what
is a typo, it should just be minus 2.
Yeah.
So in the second to last step, shouldn't it just be 6x plus 3 delta x minus 2?
Did I screw up?
Yeah, you did.
Yeah, you.
Wait,
But the answer's right.
the answer's right, but where'd the x go?
Where,
You-
no, where'd it come from? That's
You
what-
accidentally put it in when you.
Oh, I know what I did wrong. No, this should be,
It should just be minus 2 instead of minus 2.
Minus 2.
It should just be minus 2 because
X out the x.
because you didn't cancel out the delta.
that canceled with that.
Yeah.
See, the
That
two
went
delta
away.
X.
That,
That
that should be here.
Yes.
Yes, okay, sorry,
But
sorry.
it should just be a 2.
Sorry, there should be a delta x.
No.
No, just a 2. Just 2. There should be a 2.
Yes.
No x.
Yeah, you factored out the delta x.
Right, thank you. Thank you. I can understand why that would cause some confusion. Okay. Amidst my screw up, are we good?
Yes.
Okay, and again, that bothers people because you think when you take a limit, I have to get a numerical value. Every limit, just about every limit we've done, we end up getting, 2, -5, infinity. Here we're getting an actual equation. Now, think back to that picture that we had, where we had that red line. If I move that red line around the curve, the slope of that red line is going to change, correct? That's why this has an equation here. Depending on which x value I choose will change the slope of that red line. In this particular example, I chose 4, 40, which means at x equals 4, it's going to have a slope of 22. Now, why 22? Because I put 4 into the equation. What if x was 0? Then I'd have a slope of -2. What if x was 100? I'd have 598 as a slope. That's fairly steep. Okay, let's take a deep breath here. Are we good?
Yeah.
Sure.
Any problems?
Where did the 6x minus 2 come from?
When I plugged in 0 for delta x, this term goes away, and I'm left with that. What are the, go ahead.
140.
Oh, that's the point that you were given in the original
So
problem.
that's the next one.
What did I ask you?
That's
Find
an x.
Find the slope of the tangent line at the point 440.
Oh, okay.
Okay. What are the 2 things you need for the equation of a line?
Point and a slope.
Point and a slope. Oh, look, I have a slope. I have a point. I'm assuming that you can all do the equation of a line.
Yes.
Good. And leave it in that form. Don't get over the whole slope-intercept thing. was fun, wasn't it?
No.
Yeah.
Come on.
I know, I'm jumping
I understand. All right, we good? Oh, I'm exhausted. There's a summary of what we just did in a different form. Now, what's the different form? All I did is change the x's to c's. Okay. Because that's a common way that they talk about it. Instead of talking about all the x's, they'll give you a domain and then have you choose a c inside that domain. Exact same thing though. X comma f of, c comma f of c instead of x comma f of x. Michael.
So you just want us to keep the equations of lines and slope?
Yeah. Oh, keep it in whatever form you have it in originally. Don't manipulate one into the other.
Okay.
The weird thing is on the AP test, if you do that and screw it up, you're going to lose a point. And a point's kind of important. So don't leave yourself open to that kind of mistake. Okay. We good? Now that whole, yes sir.
No, I'm just asking, did it say something different for secant?
No,
It's the same one?
no, we don't do anything. We're done with secant. We just use the secant to get the tangent line. Everything from this point on becomes tangent. Tangent, 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 tangent. No secant. Or minimum secants, I should say. Because we'll do a little bit of secant because we're still using the secant to get to the tangent. But then eventually will be no secant, all tangent. Sometimes weird things happen. There are certain graphs where if you take that tangent line, that red line, and you slide it along the curve, it might do one of two weird things. It might go horizontally, which is good. We like that. We're going to do a lot with that. Or it might turn vertically. Bad. We don't like that. What's the slope of a vertical line?
Undefined.
Undefined. So what do we do with it then? Think about that line. If we go from horizontal, it slides down the curve and eventually gets to undefined. Why is the slope of this vertical line undefined?
Because it's vertical.
And yes, but what makes the slope undefined?
Divided by 0.
0 in the denominator. And how do you get 0 in the denominator? Yeah. So if you take a fraction and you have the denominator get really, really close to 0, what happens to the whole fraction? What does it go to? How big? Infinitely big, correct. So again, think of it this way. I start with a line that's horizontal, and as I start to increase the slope, the number gets bigger and bigger and bigger until I eventually get to this, which is undefined. But right before I got to that, it has a really, really steep slope. And how steep? Infinity, or negative infinity, depending on which way you come from, which leads us to this. If you do that whole limit thing, and you get an answer of infinity or negative infinity, then that tells you have a vertical tangent line. Because it's not going to spit out undefined. It doesn't work that way. But it will spit out infinity or negative infinity. And like I said, if you go from that, increasing that slope over and over again, eventually it's going to get really, really close to infinity. And because we're taking a limit, that's what it's going to give you for a function. Okay? That looks like that. And initially, you look at something like that, it's like, well, why do I care? You don't right now, but later we'll put some puzzle pieces together and you'll see that that is a fairly important scenario we've got going on there. It's called the point of inflection. But that's a long way away. Pat?
What about like when it's going to an asymptote and it's going like that to
Similar thing, but the difference is because it never touches the asymptote, you can't have a tangent line at the asymptote. So same thing happens. The slope gets bigger and bigger and bigger and bigger until it gets to that vertical asymptote. But again, it's an asymptote because you never touch it. Here, you actually have a point there where you have a tangent line. Okay, because the tangent line has to always be to a point on the function itself. Okay, good question. All right, we good? Again, this isn't a deal breaker. It's just another thing that's going to pop up every once in a while. All of that business we just did introduces something called the derivative of a function, which, as I mentioned, we're going to spend quite a bit of time doing. So we have to start by getting some terminology under control. This thing that we just deciphered is the actual derivative of a function. And what's a derivative? Well, this. And what does this represent? Before I put this slide up there, what did we find that this represents? Slope of the tangent line. That's the first thing you need to remember about a derivative. A derivative, it will serve three purposes for us. The first one is today, it's the slope of the tangent line. Okay. Now some notation. This is too much to write out over and over again, so we abbreviated it as f prime of x. That's how that's read, f prime of x. It's a little apostrophe. Oh, and this whole process we're going through to find the derivative is called differentiation, or taking the derivative. Now, if that wasn't confusing enough, you get a history lesson. You got this? Okay. All you had to do is take that other thing and put a picture in front of it. Okay, I said that f prime of x. Now you got a whole bunch of different ways to say the same thing, and I'll explain why this happens in a second. All of these mean the exact same thing. It's the derivative of the function f. Most commonly, we'll use this one. We'll also use this quite a bit. So this is read dy over dx. And then as you move to the right, the popularity decreases. Okay, y prime, the derivative of f of x with respect to x, and then this weird, strange thing over here. Okay. Like I said, dy over dx and f prime are the most common. Blah, 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 blah. Great. Okay, now why do we do this? Two guys. Isaac Newton. Everybody know Isaac Newton? Raise your hand. What did Isaac Newton do? What's that?
Didn't he invent calculus?
Yes. Well, we think so. We're not sure, though. I'll explain in a second. Also did some physics stuff. 3 laws of motion and apple on the head. You ever seen this guy before?
The guy that's on our Scrooge page.
Yeah. Check that hair out.
Luscious bananas.
It is a lot. Oh. Could be the best thing I've heard all day. In case you didn't hear me said, a luscious mane. So it's a sad story. I know everybody thinks that Isaac Newton was a nice guy. It's a lie. He was a major jag. So Isaac Newton, way back when, mathematicians and scientists like Isaac Newton were kind of like rock stars. Okay. So he was very popular. He was in charge of this International Math and Physics Society, oversaw that. He was a bigwig. And then there's this guy, Gottfried Leibniz, or Leibniz, depending on how you want to pronounce it. So what happens is, they're in different parts of Europe, and they both come up with calculus at about the same time. Now, how that happens, no one's really sure. How does a guy working over there, I think he's German, I'm not sure.
Sounds German.
And I think Newton is British. One's in Britain, one's in Germany, and they're doing their thing, and they both come up with calculus. That's why we have all of these. Okay. So Newton, I think Newton was this notation. He did dy dx, and Leibniz did this one, f prime of x. And then some other jamokes threw this other stuff in there, just to confuse things. So Leibniz, a little lonely guy, doing math, like most of us mathematicians are. And he says, hey, I found this cool thing. And in the meantime, Newton also said, hey, I found this cool thing. And so there's some accusations that maybe one stole from the other. But Newton is in a position of power, and he's kind of pissed that Leibniz came up with this huge thing that he discovered. And so he makes it his goal in life to ruin Leibniz, and pretty much does. Just, he died poor and broke, and it's a sad story. And this guy he's in every book with an apple hitting him in the head and doing physics stuff. Okay, so that's why that started. Let's get ready to rumble, because they brought over. And because he had all the cool friends, and this guy was by himself in his attic, he lost, he won. Everybody thinks he's a hero. He's actually a jag, and this guy is just poor little Leibniz with that luscious mane. Okay, so that's why there's all those different notations. Are you ready for this?
Doesn't matter, are we gonna not do it if we are?
So you don't have to do it. It's America. Like the power right on. Okay. Well, I want to find the derivative. We won't do it. Let's just talk about doing it. Okay. How would I do it?
You would find the slope of the tangent line.
Good. How would I do that?
With
Oh, yeah.
Right. Okay, so you would use that formula, come to this function, plug in x plus delta x for x, so I get x plus delta x cubed plus 2 times x plus delta x, minus the original function, in parentheses, x cubed plus 2x, all over delta x, multiply your brains out, distribute, cancel, and end up with an answer. Okay. That answer, by the way, would be 3x squared plus 2. Some would find that frustrating, because you'd have a list of terms about this long, and then when you're done, down here at the bottom, you got 3x squared plus 2. Okay. But it's the nature of the beast. That's how it works. So we're not going to do that because nobody really wants to multiply out a cubic, right? But you could, yes?
Yes.
Pascal's triangle, maybe? Or do it the hard way? Pascal's triangle? Some of you look like I'm looking at me like I'm speaking Italian.
I remember.
No? 1, 3, 3, 1?
Yeah, sure.
Oh, good. We'll just move on then. All right. Now, how does differentiability and continuity connect? So you'll recall back when you had geometry, we had a logic unit and we talked about 4 logic terms. Converse, inverse, contrapositive, so there was these 3 terms in geometry, converse, inverse, and contrapositive. You, at this point, probably have no idea what I'm talking about because you don't remember. But the important one was the
I'm sorry,
Certainly.
so is the derivative 3x squared plus 2x?
No, just 2 plus 2.
I'm supposed to, yeah,
Yes,
that's just the
that's
derivative,
the
you don't have to
derivative.
plug in anything.
Well, no, I mean, you would, but I just happen to know what the answer is.
Okay.
Yeah, I saved you the pain.
No, I
back.
meant like you didn't have to plug in the point, like how.
No,
we
no,
did
no, no,
before.
because I don't think I gave you the point.
Unless you
Okay.
put it, like, in front of the whole class.
So, what time are we done here, by the way? Oh boy, I'll talk faster. So one of the things I'm sure you remember from geometry is that if you have a true statement, then its contrapositive must also be true. Right? If an animal barks, then it's a dog.
That's
Right?
Yeah.
The converse would be if an animal is a dog, then it barks. Right? Is the first statement true?
Yes.
If an animal barks, then it's a dog?
Mm-hmm.
No, that's false. Seals bark. But the converse is true. I'm sure there's some weird dogs out there that don't have vocal cords, but dogs bark. Okay? The contrapositive is also true. In the contrapositive, you switch it and negate them. Now, the only reason I mention that is because it comes up here. So, if we do all this business, blah, 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 let's get down to this guy, then change that. Okay, great, where are we? Oh, wait, hold on. I'll come back to that in a second. I want to get to this before you go. Okay? This is important. If a function is differentiable, then it's continuous. In other words, if you can take the derivative, it has to be continuous. The converse is not true. Just because a function is continuous doesn't mean it's differentiable. Okay? We're going to stop there for today before your brains melt. We'll come back and look at the previous slides because we need to explore this idea a little bit more and look at the contrapositive of this also. But you should have a good enough chunk of information to get started on, day 18 for tonight. Okay? Nice job today. It's always better when you guys figure things out and I don't have to.